Okay. Thank you for coming, Francesco. We have the pleasure to have today Francesco Pausata from Université du Québec à Montréal with a very, very exciting talk for a very complex region, Sahara, and very comprehensive talk from the past to the future. Francesco is an associate scientist, associate professor at the Université du Québec, and his career started in Italy till a master at University of Bologna, and then followed by a PhD in Norway, in Bergen, and a couple of postdocs until he got to be the big modeler at the University of Quebec, looking at super interesting stuff from a very comprehensive point of view. Welcome, Francesco. I'm looking forward to this talk.
Thank you very much for the presentation and for the invitation to give a talk here. So today I will present the climatic impacts associated with the Green Sahara periods in the past, as well as the changes induced by future vegetation changes over Northern Africa, because I don't know if you are aware of, but there is a project that started, I think, in 2007 called like the Great Green Wall. So the aim is to build, we will see later, like a sort of a wall between the Saharan Desert and the Sahara Desert and the tropical region, so over the Sahel. So this is like the, sorry, there is like a problem. Oh, this was supposed, let me just get in again. Yeah, this is supposed, this is the outline of the talk. I will, the presentation is divided in two main parts. The first part, I will be focusing on the past changes associated with the Green Sahara. In the second part, I will present some more recent research from a study I'm doing with my PhD student, Roberto, on investigating the impact of this geoengineering project called the Great Green Wall. Okay, so in the middle of the Sahara Desert, now we can find proxy that confirms that the Sahara hasn't been always inhospitable, and actually in several different animals, mammals were living over there. Here is a map of northern Africa, and we can see, like in a cave over here, we have a cave with rock paintings and drawing of humans, animals like giraffe, lions, like for example in here we can see lions, giraffe. And these caves were discovered by Heinrich Barth, a German explorer of Africa and a scholar, which discovered these caves in 1850. And he wrote on his book that artworks bear testimony to a state of life very different from what we are accustomed to see now in this region. Barth attributed the petroglyphic to the Egyptian civilization or to some other indigenous people, arguing that this artwork must have been created long before the arrival of camels in Northern Africa, because in fact we cannot see any camels drawn in these caves. No? And this is another example of drawing in the caves. You can see in the caves right now are in the middle of the desert. So Northern African hydroclimate has been characterized by an alternation of prolonged droughts and wet periods with abundant rainfall that are termed like Green Sahara period or African humid periods. The figure here shows a marine record of barium to aluminum ratio in the Eastern Mediterranean, which is a proxy for wet and dry Sahara. Here we can see the time, the ages in thousands of years from 200,000 years ago till present. And here we can sort of what we can use it as a proxy. So high value means that the Sahara was green, low values, the Sahara was more of a desert. And here we can see all this Green Sahara period throughout the last 200,000 years. And here is just for you to have an idea. Here is the month and here is the latitude. We can see how the insolation changes between 10,000 years ago, so during the last Green Sahara period, and today. And we can see the increase in summer solar insolation here, and the decrease in winter insolation, and decrease in summer insolation in the southern hemisphere. In this slide, we can see the climatological annual rainfall for present day, and the one inferred from the last Green Sahara period in the middle Holocene. So the last Green Sahara period went from 10,000 to 5,000 years ago, together with the vegetation type that, and also the lakes that there used to be. For example, this one is Lake Chad, and this one, what it was like a Lake Mega Chad. Different type of proxy are all supporting the fact that the Sahara was a mesic environment, sometimes in the past. In this one, on the left, we can see the changes in lake stand across Africa. We can see that the lake level were much higher relative to today across the entire Africa. And here we can see on the right, we can see an estimate of annual precipitation changes due to the during the Green Sahara period, inferred by using pollen records. So we can see an increase of around 400 to 600 millimeters per year. So if you look at the model, well, the model are not showing, are showing a wettening over. So this is the mean annual precipitation, the middle Holocene minus the pre-industrial. The model do see an increase in precipitation. However, if you look carefully over the Sahara, we can see that the increase of the Sahara is smaller than 50 millimeter per year, which is for sure not enough to provide a notable vegetation change in the Sahara. However, we need to know that this model most of this model account only for orbital forcing changes. They don't account, but we know that in that period, the Sahara was greener, so there were feedbacks from the vegetation and many other feedbacks going on beside the orbital forcing that was the trigger for the change. So in their seminal paper, Kutzbach et al. In 1996 proposed the vegetation and soil feedback as an important feedback in enhancing the West African monsoon response to the orbital forcing. They only found a maximum increase of about 28% when you replace the desert with grassland and consider it also a loamy soil, which is still insufficient to explain the Green Sahara. Nevertheless, the point was that the feedback are crucial to able to understand such wet to dry transition. And this transition may consequently not be as smooth as the orbital forcing. More recently, a study in which from Deepak and Dick Peltier, the author explored here the combined effect of vegetation, soil, and lake on mid-Holocene precipitation. They use a couple models, CSM Toronto. They show that in contrast to a previous study that have explored the individual impact of this feedback, CSM Toronto yields a much better increase in precipitation in response to the collective effect. So here we just see the change between the orbital forcing, mid-Holocene orbital forcing and present day, we see an increase in precipitation. But when we actually consider the vegetation change, the soil change, and also the lake, then we can see that the increase in precipitation is much stronger, and we get significant precipitation also over the Sahara. However, until very recently, another feedback that could play a key role had been completely neglected, because we know that if the Sahara is vegetated, it means that the main source of dust in the world is pretty much gone. Dust emissions were indeed reduced by 70 to 80% relative to today. And in this study, it was published in 2016, we investigate for the first time the role played by dust in affecting the intensity of the West African monsoon. So if we look at only the orbital forcing, again, this is in millimeter per day, the change in precipitation in millimeter per day between the orbital forcing, mid-Holocene orbital forcing and the pre-industrial, we don't see a large increase over the Sahara. And the monsoon, the northward extent of the monsoon just is shifted like 200 kilometers at most. But when we consider the vegetation change and we reduce the dust, well, then the monsoon managed to expand all the way to the northern side of the Sahara. And here in a study with one of my PhD students, Shivangi, we compare different climate models in which not only orbital forcing are considered, but also additional forcing, like, for example, vegetation in ICSM and dust as well. In EC-Earth as well, we consider vegetation and dust changes. In CSM Toronto, as I mentioned, we have the lake and vegetation, but no dust changes. And then in GISS, we also have vegetation and so we can see that all this model, this is only orbital forcing. So they show a little increase in precipitation over the Sahara. But when we go and we actually implement the changes in vegetation, the changes in lake, the changes in dust, well, we can see that the amplification is much, much larger. So all models agree. GISS is the model that shows the smallest increase. So the take-home message of the very first part is that when simulated the Green Sahara period, vegetation, soil, lake, and dust feedback have a major impact on the strength of the West African monsoon. In EC-Earth, we see that the vegetation feedback play 2/3 of the northward shift, accounting for 10-degree latitudinal shift, and the reduced dust account for other like 500 kilometers for the northern shift. Then, if you look at the impact of the far-afield impact of the changes in vegetation over the Sahara, or the changes in strength of the Sahara, so we can see here the changes in a sea surface temperature standard deviation, so the variability of the sea surface temperature over the Pacific Ocean. So we can see that only orbital forcing lead to a decrease in variability over like the Niño 3.4 area of about 10%. When we green the Sahara, we can clearly see that the variability is further reduced. And then if we green the Sahara and reduce the dust, we can see that there is a further decrease in the ENSO variability. So the point here is that the Sahara greening, and so the strengthening of the West African monsoon, is able to suppress ENSO variability because the change in the strength of the West African monsoon affect the worker circulation and consequently the trade winds in the Pacific. It sort of shift the worker circulation west, and this is also this is responsible for what we see in this model. We also look at the different models, so to see, we have these 4 different models to see if the model agree. We can see, as I mentioned before, there's the same plot, there's just a different color scale and everything. Here is EC-Earth, the changes in sea surface temperature variability when we only change the orbital forcing. So the change is pretty small, there's a small reduction. Also CSM Toronto shows a small reduction, but actually ICSM and GISS show an increase. So there's no very nice agreement, I would say. But then if you look at the effect of the Green Sahara, well, the Green Sahara, 3 out of 4 models show actually a decrease in ENSO variability. Then if we take the difference between these plots here and this one here, so to just like separate the effect of the Green Sahara, and then what we have here, all model agrees that the Sahara greening, so the further strengthening of the monsoon at the end of the day, lead to a reduction in ENSO variability. So there is some agreement on that. Then, if we look at another teleconnection, the tropical cyclones, here let's see how the Sahara greening can affect the tropical cyclones. So here I show the track density of tropical cyclone as simulated by the statistical model driven by EC-Earth. So we can clearly see the area with like yeah, the typhoon area, tropical cyclone area, hurricanes area here. And then if we look at what happens in terms of changes in track density during the mid-Holocene, when we only change the orbital forcing, we can see this dipole here, decrease offshore, increase inshore, and the same things happening here. So we can sort of see this shift westward of the tropical cyclone activity is likely related to the worker circulation shift that I mentioned before. And then if you go at the Green Sahara reduced dust scenarios, minus pre-industrial, that we can see that the pattern is the same, but the anomalies are enhanced. And also in the Southern Hemisphere, fun, interesting things. Even though the summer insolation, by the way, in the summer in the Southern Hemisphere is actually decreased, but the effect of the greening of the Sahara and the strengthening of the monsoon is seen also in the Southern Hemisphere. Then the last teleconnection is the Indian summer monsoon that we've been looking at. So here we see that the Indian summer monsoon strengthened due to the orbital forcing change, not much, but we can see a, a slight increase. But then when we green the Sahara, reduce dust or do not reduce dust, but we put lakes. Anyway, we strengthen the goal here, we strengthen the West African monsoon, and voila, we get like a strengthening of the Indian summer monsoon as well. So to summarize this part here related to teleconnections, so the strengthening of the West African monsoon under Green Sahara condition triggers a sort of an Atlantic Nino, which suppresses variability that shift westward the worker circulation, leading to a decreased ENSO variability and Nino-like condition in winter. The Sahara greening and dust reduction can also affect tropical cyclone activity. And finally, we have seen also the impact on the Indian summer monsoon. Now I will briefly talk about the transition because we are not sure whether the transition has been abrupt or not out of the Green Sahara period. And I will start with the very first study, investigate the pace of this transition. It was done by Clausen and colleagues, which use a climate system model of intermediate complexity, CLIMATOLOGY, to simulate the transient evolution of the African hemisphere. So here is about 9,000 years ago, here is the present, and here you can see like the change in summer solar insolation. The resolution of the model was very coarse, was something like 10-degree latitude and 51-degree longitude. So, but it was anyway almost 25 years ago. So then here I said it's the insolation, and here we can see the changes of precipitation during these 9,000 years. And here is the change in fractional vegetation cover in the Saharan region. So we can see that while the change in orbital forcing is gradual, the precipitation, and in particular the vegetation fraction, is anything but actually gradual. It doesn't follow the orbital changes, but is much more rapid. So the climate modeling in the 90s already revealed that the feedbacks between atmosphere, land surface, and ocean can strongly amplify the monsoon and vegetation changes. And it was proposed that the African humid period could have ended and the Sahara could have expanded within just a few centuries, which is much faster, as I mentioned, than the orbital forcing alone. In fact, a year later, in 2000, Peter de Menocal and a co-worker published data from a marine sediment core off the coast of off the coast of Northern Africa, Mauritania, and around 20-degree north. And the data showed that the evolution you can see here of the terrigenous flux deposit at the site location. And we can see that there is a rapid decrease and a rapid increase of dust, of terrigenous fluxes. And here we can see the change in insolation of 20-degree north, summer insolation. So this one was like leaning towards the fact that the Sahara the Green Sahara period ended abruptly. However, a few years later, another study came out from Lake Yoa in Chad that suggested a more gradual termination of the Green Sahara period. So here we can see the onset and the end. And then, as I said, this other study from Kropeling came out in 2008 saying, well, maybe the transition from a Green Sahara to present hyperarid desert was more sort of progressive. So since then, many other studies came out. So I will just show a little summary of that. Here we can see a compilation of Northern Africa terrestrial paleo records in gray. You can see the red circles with error bar that represent the mean African humid period termination age at the given latitude. So for example, let's say at 30, the mean termination age is about almost 6,000 years ago. Here is the range of uncertainty range, here 1 sigma. And then we mentioned too high here there are too high resolution African humid period termination ages. And then in the green line show the expected African humid period termination associated with the orbital forcing. So if it would have been gradual, it would have followed this curve here. So what we can see overall is that it seems that the withdrawal of the African humid period on average occur following the insolation changes, but not everywhere. So locally, the changes might have been abrupt. So if we then look at a very recent modeling study by Dalmey and et al., is the Martin Clausen group, we can see the biodome distribution here on the left based on the simulated plant functional type for the Middle Holocene and the pre-industrial. So we can see like this, the savanna expanding north, and also, you know, like the grassland here. There is still quite some desert in the simulation. Probably there was less desert than actually in their model. And so yeah, this one is so in this two panel on the right, instead we can see the simulated minimum desert fraction during the Middle Holocene. So we can see that here, for example, in present day, we have a desert fraction of 1 because it's all desert. But here in the Middle Holocene, we can see that the desert was really confined to a smaller part of Northern Africa. Finally, if we focus on these 4 grid box here, like we look at this grid box here, and then we look at the simulated change in the plant functional type cover fraction, so grassland, desert, shrub, and forest fraction from 8,000 years to the pre-industrial for those 4 grids. We can see that some of the plant functional type changes are indeed more abrupt, like we can see like this abrupt increase in the desert, or like this abrupt decrease in the grassland, and the same here and here. And instead at other latitude, like northern latitude, was a little bit more gradual. So we can see this one. So if we put together this recent modeling studying output with the synthesis of proxy archive that we saw before, we can say that while some paleoclimate archives show changes that took place over several centuries, which is an order of magnitude faster than the orbital forcing, others show a much more gradual change. The withdrawal of the African humid period was overall time transgressing following the insolation change, so went from north to south. New transient climate simulations show spatially heterogeneous vegetation dynamics in Northern Africa. The fastest increase in simulated desert fraction, up to 7 times faster than the orbital forcing, occur around 20 degrees north here in the western part, and around 14 degree north in the central and eastern part. Because of the spatial heterogeneity of the African landscape and African monsoon circulation, abrupt changes can occur in several, but not all regions at different times during the transition from humid to arid period. Abrupt changes in one region can then can be induced by abrupt changes in other regions, and this process is called induced tipping point. So overall, the African humid period transition of the Sahara was regionally rapid, hence a tipping element, with respect to the change in the orbital forcing, which is the driving force. But it was overall slow with respect to the time scale of individual humans and local ecosystems. So they had the time to adjust to this change and to migrate. In any case, the African humid period transition, rapid or gradual depending on the perspective, has led to persistent and long-lasting changes that are associated with the tipping point in human civilization, which led then to the emergence of new cultures along the Nile. So this is all for like the past, and now we'll dive into the future, let's say. So let's talk a little bit about the Great Green Wall, but first we need to take a step back because the Great Green Wall idea was actually proposed already in 1935 as a forest belt between the Sahara and the Sahel. And the idea was to reduce the southward movement of sand and also man-made soil erosion. In 2007, the Great Green Wall initiative was officially adopted by the 11 founding members at the conference of the head of states and government of the African Union. And so the idea is the Great Green Wall will extend from Dakar to Djibouti, so from Dakar here to Djibouti over here, which is about, it's more than 7,000 kilometers in length. And the idea was to have a wall that was wide about 15 kilometers over south of the Sahara. However, this idea evolved since then and is now aiming at more at restoring the degraded land towards a more sustainable agricultural practicing. So it's not anymore like 15 kilometers, but it's actually more. And as I said, it's trying to like restoring the degraded land. So it aims at expanding the vegetation in the central and northern part of the Sahel, in particular in the area where the precipitation is between 400 and 100 millimeters. So it's about 4 to 24 inches for the people that speak in inches of annual rainfall. So the main, let's say, well, one of the main objectives of this project is to ameliorate the local climate condition, but also contributing to the adaptation and mitigation associated with climate change, and also contributed to the economical growth and development of those nations at the end of the day. So what we did is, as we realized that there was not many studies done on what are the potential impact of this big project, because eventually it's a geoengineering project. We start planting vegetation across like 7,000 kilometers, the entire Northern Africa or entire the Sahel. So what we did is we tried to sort of create in our models this Great Green Wall, following the Sahel borders, and particularly the rainfall climatologies, and we implemented a mix of woody and herbaceous species, which properties and characteristics that are somehow similar to those proposed and used in the Great Green Wall. For example, depending on the precipitation climatologies, a different mix of desert, shoregrass, evergreen, and deciduous shrub is used. Now you can see, like in this area, between 100 and 200 millimeter, we put like we leave 25% of desert, 25% of grass, and so on. Instead, if we move more to the south, where there is more precipitation, we limit the desert to 15% or even to 5% when we go between 300 and 400 millimeter. But then we wanted, okay, to look at this one that is a more realistic case, but also we decided to do a more like extreme cases where we actually extend the northern limit not to 100 millimeter, but actually to 50 millimeter. So we use a model with a resolution of 13 kilometers. So we downscale it with we did a dynamical downscaling with the model at 13 kilometer resolution. So we perform a simulation of a present day climate for 1971 to 2000 and two for the future, like RCP 2.6 and RCP 8.5. And here what I show is the change in precipitation, in total precipitation, due to the associated to the change in greenhouse gases, RCP 2.6 or RCP 8.5. And we can see that the changes in precipitation are restricted over this area. There is a slight increase and a decrease over like the Senegal, over this part here. For the RCP 2.6, which is the most optimistic, if we manage to stay within the 1.5 degree or yeah, more or less. And this one is in the case of the changes in precipitation where when we implemented, so between the Great Green Wall simulation and the RCP 2.6. So on top of what we see here, we will get this anomaly. So here there is no much anomaly. So, but anyway, on top of those, of that nothing, we get this this change in precipitation. So we can see that all the Sahel region, but even further south, we can get an increase of up to 100 or even 200 millimeter, which is quite a lot. If you think of the climatologists, that area that, as I showed you before, it's of the order of 100 to 400 millimeters. So we sort of even doubling the amount of precipitation falling in the region. And if you go on the extreme case, well, you can see that it extends, the amount of precipitation increase extend well into actually the Sahara Desert, although the Great Green Wall stops here pretty much, the extreme. So we can see that the far field sort of impact, I mean, relatively far field. And this is for the 2.6 scenarios, and for the 8.6 is a very similar scenario. Actually, if we increase the temperature less, the precipitation will actually, we will see the temperature rain very soon. We actually increase a little bit even more the precipitation. So if you look at the temperature changes, well, for the RCP scenarios, we are limited at about 1 degree to 2 degree summer increase in temperature. And if we go on the 8.5, it's going to be a disaster with like 4 to 5 degrees increase in temperature during the summer months. And then if you look at instead of the impact when we put this Great Green Wall, so this is the change again of, in case of the Great Green Wall, on top of the change that we see here. So here we see an increase of about 0.5, 0.075 to 1 degree. And here, because of the Great Green Wall, we can see a decrease of up to 1.5 degree. So it sort of would like cancel out this increase in temperature, the Great Green Wall. If we go on the extreme cases, we can get even like a cooling, actually a net cooling, although even with an increase in temperature during the summer months. And this is for the 8.5 scenarios, the same things. We get this this cooling, which is a little bit larger, but not much, due to the Great Green Wall. Okay, but let's now look a little bit at the extreme. In particular, let's look at the consecutive dry days. So what are the consecutive dry days? Are the consecutive days with precipitation below 1 millimeter, which give us an indication of the length of the droughts. Another index is the stream rainfall over a 5-day period, which is also very important because we want the precipitation not to get more extreme in a short amount of time, but to get just more precipitation, like better distributed over time. So let's have a look at the consecutive dry days. The consecutive dry days decrease, which is very good. So this measure is sort of effective, in particular over the central and western part of the Sahara, a decrease of up to 30 to 40 days, so 1 month less of drought over the Sahel region. And in terms of extreme, yeah, of course, the 5 days precipitation extreme increase a little bit, but it doesn't seem dramatic. And then if we look at the extreme in temperature for the temperature, so we look at the change in maximum temperature extreme, So although we have seen a decrease in the summer temperature, we actually have a net increase, well, like an increase in the extreme compared to this one. Or so this one is sorry, here there is a mistake. This is a 2.6. It should be a 2.6 scenario. Those plots were done a few days ago from my PhD student. He probably just forgot. He put 8.5, but it should be 2.6. This is the 8.5. So we can see that because of the increase in greenhouse gases, we have an increase in the maximum temperature extreme. So instead of being 40, it's going to be something like 44 or something along those lines, or even more. In this case, when we put like the gray-green wall, well, the extremes increase even more compared to the RCP scenarios. The same here, even more for the RCP 8.5. The greening of the Sahara is going to boost even more the extreme in temperature of a couple of degrees more, of already like 5 or something degrees extreme increase here. So how is that possible? How is that possible? Actually, we saw a reduction in temperature in the summer months, but it's because the maximum temperature and the hot extremes are not actually recorded in summer, but actually are recorded in the pre-monsoonal season. So, and the fact that we change the vegetation, so we change the albedo, we absorb more radiation, and so we actually are going to get like stronger extreme, higher extreme. So here what we see is the seasonal cycle of temperature, maximum temperature. So we can see, let's focus on the present day, on the black line here. So we see increase till May, and then June, July, August, the temperature decrease, then increase slightly in October, and then decrease. This is for the Sahel region. So if we go on the 2.5 scenario, which is the dashed line here, we can see that the temperature is higher all year long, except from June, when it starts being lower compared to the present day. This is the extreme cases, the dark green, and the light green instead is the normal green wall, but the behavior is pretty much the same, particularly in the first part of the season. It's lower, and then it becomes higher. And we can see it even worse in the case of the RCP scenarios here, the 8.5, RCP 8.5. Here is the only greenhouse gases. And then, you know, the decrease is stronger, but also is the increase in the pre-monsoonal season. So we can get like extreme maximum temperature of the order of 43, 44. Sorry, this is not extreme, this is just the mean temperature. So we would pass from a mean temperature of the Sahel of 38 in the pre-monsoonal to 42, to something like 42. So, okay. So the take-home message of this last part, and then I'm about to conclude, is the gray-green wall has a significant impact on Northern Africa, increasing rainfall over the entire Sahel, even doubling precipitation in its northern part. The consecutive dry days are substantially reduced, and the max 5 days precipitation are increased in the equatorial and tropical Africa. The temperature around the gray-green wall are decreased of up to 1.5 degrees in summer, and over 2.5 in the extreme cases. However, the hottest temperature become more extreme of up to 1.5 degrees. The impact, well, I haven't shown this one because I really focus over Northern Africa, but the impacts are not confined to Northern Africa, but extend well into Southern Africa and even in Southern Europe, the Mediterranean area. We are going to look into more details in the following up study. So to conclude, Here is just like a schematic slide highlighting how changes in the vegetation and land use, lake, dust, and so on over Northern Africa can affect the intensity of the African monsoon, which in turn can impact El Niño, tropical cyclone, other monsoon system, and even the Arctic amplification, even Arctic climate. And I think with this slide, I conclude. Thank you.
Thank you, Francesco. It was fascinating. I would like to give the opportunity to people to ask questions if they want, directly or in the chat. Until there are questions, I would like to ask one.
Yeah.
As we discussed before the presentation, Southern Africa has an equivalent but smaller desert, the Kalahari, and a huge lake in glacial periods. And it would be fascinating to see if they have similar effects on feedbacks on both between each other. As you said, the green wall has effects in the south. So what's happening in the south might transfer to the north, or if the Kalahari has any effect on feedbacks on monsoon in Australia, or it's more of a comment than a question. In any case, the presentation here shows that it's not that simple with only orbital forcing and thinking.
That's exactly, exactly. And I think it would be definitely interesting to actually look at also the impact of the Kalahari Desert. What would be the impact of let me see if I can find something regarding, because as I mentioned, we did some areas. So we look at actually the impact of. So we focus, for example, let me just open it here. So
the generalizing things is this dust sources. Even I'm thinking Australia now.
Yeah, exactly. Yeah, there is Australia. There is the Kalahari Desert, which is also another source of desert. And here we just, for example, show the impact of, even in southern Africa, we can see the impact. This is only orbital forcing, the changes in temperature, and when you consider also the greening of the Sahara, that is like not here, but you can have like actually feedback here. So I would expect that if you change the vegetation, you change the lake here. You told me that there was a mega lake here.
Yeah.
So I mean, I'm 100% sure that we are gonna see something for sure at local scale, but local scale, I mean, at least like regional scale. So it would be definitely interesting to have a closer look at your data when you will get it, and then do some modeling.
What is fascinating is that these feedbacks are not small.
Yeah.
I mean, Sahara is huge, but Kalahari is also huge. Australia is also huge.
Yeah, exactly. So
these are things that are on the same size. The changes, the feedbacks in vegetation, dust, and lakes, as big as the orbital.
Yeah, totally.
It's fascinating.
Thanks.
Well, I see that there is a chat question. No, it's just thanking you. Dulce Rivera is thanking you. Any questions, please?
Paul may want to.
Francesco.
Hello.
Can you hear me?
Yes.
Oh, great. So, first of all, apologies. I arrived late to your talk. I got interrupted coming here, which is a real shame. But I have 100 questions because it's very, very, very interesting stuff. One thing that interests me regionally is in a lot of your simulations, the northeastern Sahara appears stubbornly dry, or it's the last place to change. In contrast to, I mean, obviously it's furthest from the West African monsoon. What's your, it's an interesting observation that today, it's often said that the Sahara is where it is because it sits under the descending limb of a Hadley cell. But, the irony is that the Sahara is driest when vertical motion is weakest. And it's been speculated that part of the answer is teleconnections associated with Rossby waves downstream of Asia, and so on and so on. I'm just kind of interested in, from the dynamical side. What's your sense of how coupled or uncoupled the Eastern Sahara and the Western Sahara really are? But in the hydroclimate response to forcing?
This is a very good question, because we do see that the response is stronger on the Western one, as you mentioned, than the Eastern part. But we do see also that the Eastern part is getting greener. It's just that, yeah, it's true that also the records show like that the desert, the last part of the desert were actually confined probably to the northern eastern part. The reason why, and well, I mean, this is because I don't know how the East African monsoon is actually, yeah. I don't know exactly why the eastern part of the northeastern part of the Sahara keeps because I guess it's less affected both by the East African monsoon, because the East African monsoon is sort of stopped at the Ethiopian highlands over there. So it's sort of stopped there, and then you sort of have a kind of a rain shadow. And then the West African monsoon is, of course, more to the western part of the, so when the moisture try to get in, it's sort of it's rain out the moisture. So I would say that that's the main reason why the northeastern part is drier. But I'm not sure if it was that the question that you were looking for. I mean,
well, I think it is a tricky question. I mean, a sort of related question is whether, in your work, you think, have you seen any signs at all that there's the winter rainfall season, the Mediterranean westerlies could play some role in responding? I mean, I guess the kind of Eastern Med is predicted to be a real hotspot for sort of drying.
We did see it's funny. I mean, we see a reduction in the pressure over Northern Africa during the winter months, and a slight increase in precipitation again more on the western side. So I mean, of course, it's just a model. So the increase in precipitation is about 10% in the winter months. But my idea, like looking at the general circulation changes, I would say that it's more like of a negative phase of the NAO. So there are possibility of more storm actually getting into the northern part of Africa. So I'm leaning also to the idea that the winter precipitation may have changed and being higher during during the Green Sahara periods. And this is one of the things that actually I would like to look at a little bit more in details.
Yeah. Okay. Well, like I said, I have 100 questions, but those were the two that were top of my list.
Yeah, but to email me, and happy to discuss more. I mean, really, yeah.
Thanks a lot. Yeah, it would be good.
Thank you, Paul.
Ciao.
Ciao.
Any more questions? If not, I would like to thank you, Francesco, a lot for this incredibly interesting presentation, and thanks for participating in the seminar.
Thank you, Livio, and we'll be in touch.
We'll be in touch. Bye-bye.
Bye-bye.